Differential protection has one job. It watches a single piece of equipment and it asks one question. Is the current going in still equal to the current coming out? A large power transformer can cost millions and take a year to replace. A fault inside one has to be cleared in a few cycles before the damage spreads. Not seconds, cycles. And the relay has to be certain that fault is inside the transformer, because tripping for a fault somewhere else takes healthy equipment off the grid for nothing. In the next few minutes, we will build the whole scheme from one law. Current in equals current out. Then we will follow that current through a fault outside the protected zone and a fault inside it. We will see why a real relay needs a restraint, and what happens the moment a transformer is switched on. Some equipment is simply too valuable to lose. A large power transformer, a generator, or a substation bus bar, which is the metal bar that everything else in the substation connects to. So why can a simple overcurrent relay not do this job well? An overcurrent relay is a relay that trips when the current rises above a set level. That is all it knows. It reacts to any large current, and it cannot tell whether the fault is inside the transformer or far down the line. To stay selective, it has to wait and let the devices closer to the fault act first. That waiting is time the transformer does not have. Differential protection removes the waiting. It watches one zone and it ignores everything outside that zone. So how does it know where the zone ends? The whole method rests on one law. It is Kirchhoff's current law, which means all the current entering a point must also leave it. Now look at what we are protecting. A 10 megavolt ampere distribution transformer, 33 kilovolts down to 11. At full load, it draws 175 amps on the high voltage side and 525 amps on the low voltage side, 3 times as much. So the two line currents are not equal, and they never will be. That is what a transformer is for. What balances is the power, and the ampere turns in the core. So we pick the current transformer ratios in that same 3:1. A current transformer is a device that makes a small, scaled copy of the large primary current. 200:1 on the high side, 600:1 on the low side. Now both of them hand the relay the same value. Those two copies meet at the relay and they cancel. What is left over is called the differential current, and in a healthy transformer it is almost nothing. The relay that measures it carries device number 87, the ANSI standard code for a differential relay. Now watch what happens when a fault appears just outside the zone. Now a fault on the 11 kilovolt bus bar just outside the protected zone. The transformer impedance is 7%, so the fault current settles at about 14 times full load. That is 7,500 amps on the low voltage side and 2,500 amps on the high voltage side. Still 3:1 because the transformer itself has not changed. So both current transformers now hand the relay 12.5 amps. Still identical. The differential current is still 0, and the relay does not move. That is the whole point. 14 times full load current is pouring through this transformer, and the protection stays perfectly still because none of it is leaking out. Now move that fault a few meters to the left inside the zone. Now the fault is inside the zone, on the low voltage terminals, between the two current transformers. The 33 kilovolt system still feeds it. 2,500 amps still flows in on the high voltage side. But look at the low voltage current transformer. It reads 0. There is nothing on the 11 kilovolt bus bar to push current back into the fault. It is a load bus bar, not a generator. So the relay sees 12.5 amps arriving from one side and nothing at all from the other. 12.5 amps of differential current, where a moment ago there was none. Nothing outside the zone can produce that, because anything outside flows in one end and out the other. The relay operates and it trips the breakers on both sides at once. But real current transformers are not perfect, and that is a problem. Two current transformers are never perfectly matched. Their small errors grow as the current grows. During that external fault, at 14 times full load, a 1% mismatch becomes nearly half an amp of differential current in a perfectly healthy transformer. So we use a percentage bias, which is also called a restraint. The relay no longer trips on a fixed amount of difference. It needs the differential current to be a certain percentage of the current flowing through the zone. The more current passes through, the more difference the relay will tolerate before it acts. On a graph, the trip line has a slope. A common setting is 20 to 40%. Near the origin, that line is flat at a minimum pickup, so tiny standing differences are ignored. Now put our two faults on that graph. The external fault sat at 12.5 amps of through current, with less than half an amp of difference, far below the line, so it rides straight through. The internal fault sat at half that through current, with 12.5 amps of difference, far above the line, so it trips. But we have quietly assumed something about those current transformers. We picked the current transformer ratios to match the transformer, 3 to 1, and the two copies landed neatly on top of each other. Real life is not that tidy. The current transformers come from the switchgear in standard ratings, and they rarely match that well. So the relay applies a matching factor to bring the two sides together. Then there is the winding arrangement. On our transformer, the high voltage winding is a delta, and the low voltage winding is a star. That arrangement shifts the current by 30 degrees. Subtract two currents that are 30 degrees apart, and you get a large difference out of a perfectly healthy transformer. So the relay rotates one side before it subtracts. Older schemes did this with interposing current transformers, wired between the main current transformers and the relay. Modern numerical relays, which are relays built around a small computer, do both corrections in software. And then there is the moment you switch it on. When a transformer is first switched on, it draws a large one-sided current called magnetizing inrush. It is the current that magnetizes the core, and it can reach 8 times full load current. On our transformer, that is 1400 amps on the high voltage side. That inrush flows into the high voltage winding only. Nothing comes out of the low voltage side because there is no load yet. So the high voltage current transformer sees 7 amps, and the low voltage one sees nothing at all. To the relay, that looks exactly like an internal fault. Trip on that, and you disconnect a perfectly good transformer every time you energize it. So the relay looks at the shape of the current, not just the size. Inrush current is rich in the second harmonic, which is a component at twice the normal frequency. A real fault current is not. So the logic runs like this. Measure the differential current. Is it above the bias line? If it is, check the second harmonic. High second harmonic means inrush, so block the trip. Low second harmonic means a real internal fault, so trip. So where do we actually use all of this? Differential protection is the main protection for high-value equipment. Engineers call it unit protection because it protects one defined unit and nothing beyond it. We use it on power transformers, on generators, on large motors, on substation bus bars, and on short cables and lines. The name of the zone changes each time. The idea never does. Compare what goes in with what comes out. Because it acts only for faults inside its own zone, it needs no time delay to stay selective. That is what makes it both fast and precise. It is always paired with slower backup protection, usually overcurrent, in case the differential scheme itself fails. Protection engineers never rely on one device. So, a recap. Differential protection compares the current going in with the current coming out. A large difference means an internal fault. It rests on Kirchhoff's current law, using one current transformer at each end of the protected zone. On a transformer, the two line currents are never equal, so the current transformer ratios do the matching, and the relay compares what they hand it. An external fault passes through the zone, so the two still agree, and the relay stays stable. A percentage bias raises the trip threshold as the through current rises, so current transformer errors during a heavy external fault do not cause a false trip. and second harmonic restraint lets the relay ride through magnetizing inrush. Here's a question for you. What slope setting is used on the transformer differential relays at your site, and why that number? Leave a comment and tell me. Next time, we look at restricted earth fault protection and the fault this scheme quietly misses.